Hi, hello guys. Um, Here in this video, we're going to solve the question we have right there on your screen. It says a mass of 0.2 kg is attached to the lower end of a light helical spring and produces an extension of 5.0 centimeters. Calculate when you have the force constant of the spring. Then the second part of the question says the mass is now pulled down a further distance of 2.0 centimeters and released. Calculate the time period of subsequent oscillation. So here you have the acceleration due to gravity equal to 10 meters per second squared. So from Hooke's law, which is the applied force on a spring is equal to the spring constant multiplied by the extension, which we can say it's x. Some of the things I'm going to discuss here, we've talked about it in the last video, and if it seems kind of confusing for you, you can check out the very last video I uploaded. You'll have an idea of everything that I'm going to talk about. So K, okay, is Newton per meter. In case you come across a question that gives you the spring constant, so it will be in Newton per meter. From Newton's second law, we have our F equals to mg, where m, that's the mass. Here we have the m as 0.2 kg, and here we have the g as 10. What's the displacement here? That's 5.0 centimeters. If you convert that to meters, you have 5 times 10 raised to the power of minus that should be minus 2. Yeah, minus 2 meters. We know that this is Hooke's law, and the applied force is also equal to mg, and it's also equal to ma. But in this case, our a is the acceleration due to gravity. We don't need the last one. We'll just work with the kx, that's the spring constant, then the mg. So let's just equate those two to each other. That's k multiplied by, what's our x? 5 times 10 raised to the power of minus 2 meters, equal to the mass is, this should be kg, 0.2 kg. Then the acceleration due to gravity, that's 10 meters per second squared. K here will be equal to 0.2 kg multiplied by 10 meters per second squared divided by 5 times 10 raised to the power of minus 2. This should give you 40 Newton per meter. That should be one. Then down to the other part that says the mass is now pulled down a further distance of 2.0 centimeters and released. Calculate the time period of subsequent oscillations. That's the period. That's what we are asked to calculate. So how do we get the period? All right, from the expression of simple harmonic motion, which is this equals to minus kx. Now, we know that the angular velocity is equal to the spring constant divided by the mass of the spring. And on the other hand, angular velocity is also equal to 2 pi divided by t. It's not like saying it's the velocity equals distance over time. So the distance here is the circumference of that oscillating wave. Then the period, that's the time taken for that particle, that spring, to cover that said distance. Period of the spring. That's what we need from the question. So how do we go about that? Now, since these two guys, they are somewhat equal to each other, we can say that k over m, that's equal to the angular velocity squared. And the angular velocity we can slot in these guys into it. So that will be k over m equals 2 pi over t all squared. Well, this would end up becoming k over m equals 2 pi have the squared over t squared. We make t squared the subject of formula. That's 2 pi squared divided by this comes here, and these guys take their percent. That's just what we did. For some of you that might seem a little bit confused. K over m. Now if we are to square both sides, now if you square this guy, this will cancel this. If you square this guy's, the square will cancel the square root, and you're left with this. So that's t as the period equals to 2 pi over k m. And you can also rewrite this as 2 pi multiplied by the square root of m over k. That's the inverse, since you have the division there. So now we've gotten the period. We'll just slot that in to this guys right here from the question. Okay, we have m as 0.2 kg, and we have g as 10. Then we have that's 10 meter per second squared. Then we have, what is the way? Okay, we've got the spring constant as 40 Newton per meter. So we just slot that in to our equation. That's 2 pi. That's the period of the spring over k, and that will be 2 pi square root of 0.2 divided by 40. So this should give you 0.44 seconds. And one thing I also want you guys to note is that the period that we've got here is independent of the initial displacement we have from the question, which is 2.0 centimeters. Okay, it's independent of that. So in case you might think, oh, we've not used this guy, when it comes to period, it's independent of the initial displacement as required for this question. So that's it, guys. Thank you very much, and I'll see you in the next video.